All right, guys, so in the last section, we saw how we can actually take a perfect sinusoidal source, which is in the time domain, and rewrite it as a phasor. What the phasor essentially does is it turns the time domain cosine function into a complex number, right? In which we actually also omit a portion of the temporal part. The only information that's actually carried by the phasor is the magnitude of the sinusoid as well as the phase constant of the sinusoid. Now, if we happen to have a phasor already given to us, we can also, by performing an inverse phasor transform, we can actually take it and turn it back into a function in the time domain. So here in this section, I want to talk about the inverse phasor transform. So suppose that we have, and I'm taking here I as the current example. Last time we talked about voltage, we could also have phasors of different types. This one happens to be that of the current. And notice that we know it's a phasor because we've included the little tilde on the top of this. Now, this actually represents two things. The first thing is this is going to have some magnitude, and it's also going to have an angle of the form e to the j phi I, something like this, right? Notice that there's no temporal portion whatsoever. This right here is the magnitude. This is the phase of the phasor. I also want to introduce very quickly some notation. And it's notation that's going to be used throughout the course of the semester. Notice that writing e to the j I over and over and over and over again, it gets very, very unwieldy very, very, very quickly. So one thing that we can do to simplify this is anytime we see e to the j some angle, maybe something like beta, this itself can be rewritten as angle beta like this. It actually helps in terms of understanding things. However, if you actually need to go back and do some actual calculations, anytime you see that little angle symbol, you actually have to turn it back into e to the j beta, like this, right? So this phasor can be rewritten in these three equivalent forms, like this. Like so. All three of those are absolutely identical. And one of the things that we can do in order to turn it back into the time domain portion is we're actually going to take the phasor. So this is going to be the time domain portion corresponding to that phasor, is we're actually going to take the real part of the phasor itself multiplied by e to the j omega t, like this. So this portion right here was actually introduced, right? It's something that you needed to know extra. And keep in mind that it's not information contained within the phasor itself. This is something that you need to have extra knowledge about the circuit in order to actually obtain. But to get the time domain portion, it's relatively easy, right? Remember that this phasor is shorthand for the magnitude, which is assumed to be real, times e to the j phi I. I still have to multiply by e to the jt. So this still does carry along to that. Now, I can actually put both of these portions into the same exponential. So I can rewrite this as the real part of Im, e to the j phi sub I plus omega t, like so. But according to Euler's identity, so here I'm actually going to use Euler's identity here. And And so I'm going to take the real part of I sub m times cosine phi I plus omega t plus j times the sine of the same argument like this. Notice that I can actually distribute this I sub m to both of these. And since I sub m has been assumed to be real, the real part of the sum of these, well, it only consists of this part. Why? Because we have that j there, making the second part a complex number. So the real part of the entire thing is I sub m times the cosine of phi sub I plus omega t, or if you feel more comfortable just rearranging the terms inside of the cosine, this is I sub m cosine omega t plus phi sub I like this. Right? So this is now the inverse Phasor transform, and we denote it like this, of the Phasor I sub m where it is the inverse Phasor transform of this, which is I sub m times the cosine of omega t plus phi I, like this. Now, in practice, it's very, very easy to form this. Essentially, all you have to do is you're going to take I sub m, this is going to be the magnitude, you're going to add in the cosine, you're going to also add in the cosine omega t, and the information about the phase constant goes into the second part of the argument like this, and we'll see many, many examples in which we can actually take the inverse Phasor transform of a phasor, but you'll see how useful it is once we start working with practical problems.